Remember, end behavior is what your function does as x goes to positive infinity or negative infinity. When you've got really big x values, those extreme x values on the left and right ends. And what we're going to do now is we're going to look at polynomial functions, f of x equals, we'll look at a function, and we'll learn how to determine what the ends of that graph look like by looking at the function without its graph. Because our goal is going to be to actually graph polynomial functions later on. For now, we focus on the end behavior. Okay, we can see here I've got 3 different examples of polynomial functions: y equals x squared, y equals x squared minus 4, and y equals x squared minus 2x plus 1. And we're instructed to draw the end behavior for each and describe in a sentence. So let's do part A here, y equals x squared. We can see that on the right end it goes up forever, on the left end it goes up forever. So if we draw that, we might draw it like this. If we just focus on the ends of the graph, the right end does this and the left end does that. Okay, so that's summarizing what I've highlighted here. And similarly, if I look at the right end and the left end of part B, I get the exact same end behavior. Okay, the left end goes up and the right end goes up as well. And similarly, on y equals x squared minus 2x plus 1, I get the exact same end behavior. Okay, and we're going to talk about why that is. Now let's go ahead and describe this end behavior, and it's the same for all 3, so I'm going to write it once. The left end says that as x approaches negative infinity, y goes up forever, so y approaches positive infinity. The right end, as x approaches positive infinity, y goes up forever, so y approaches positive infinity as well. So now we've described and drawn the end behavior for all 3. They all have the same end behavior. The reason for that is because all 3 functions have the exact same leading term. And that's extremely important. I'm gonna type this up for you in a second, but the idea is the leading term is going to dictate your end behavior, because when you're looking at really big x values, x is going to infinity, right, or negative infinity, that leading term is going to make every other term in your polynomial, whether it be negative 4 or negative 2x or positive 1, that x squared, because you're plugging in a really big number for x, is going to make the other terms that have lower degree look like 0, look like nothing, basically, insignificant completely. So to summarize what I just said, this is the key to this finding end behavior. The key is, let me make this even bigger. Oops. The key is the end behavior is dictated by the leading term, okay? The leading term. So the leading term on all 3 of these is x squared. We know that the graph of y equals x squared looks like this. In fact, x to any even power goes up on both ends. Okay, so what I want to do now is sort of summarize the different leading terms you could encounter with a polynomial function that has at least an x term. Okay, so here we go. When you have a polynomial, your leading term, let's look at leading terms and end behaviors. Okay, leading terms and end behaviors. When your leading term is x to the first power. Now, it could have a coefficient in front of it, like a 2, all right? Or a 3, or a negative 2, or a negative 3. So let's just say we have a positive coefficient, positive x to the first. Then that is a line because it's x to the first power. you should know how to graph y equals x. I'll remind you here, this is x to the first power. It's simply a line with a slope of 1 and a y-intercept of 0. So it goes through the origin and is diagonal from left to right. So the end behavior for x to the first power looks like this. The left end goes down in a straight line, the right end goes up in a straight line. Okay, so that's x to the first power. That one's kind of unique. All right, you'll see why in a second. If you have a positive coefficient times x to any other odd power bigger than, greater than 1, well, it's still gonna go down on the left and up on the right, but it's gonna curve, right? If you look at, for example, y equals x to the third power, so that's an odd power greater than 1, we know that the graph of that function goes down to the left and up to the right, but in a curved fashion as opposed to a straight line fashion. So the ends of x to an odd, well, the left side, the negative values are negative, and the positive values are positive y values. Okay? And if you've got a positive number times x to any even power, well, when you have x to an even power, you're going to get positive numbers on the right and positive numbers on the left. As opposed to an odd power, you're going to get negative numbers on the left, positive numbers on the right. Okay? So those are really the three end behaviors for a polynomial function. But your coefficient in the front could be negative. So if you go back and you look at the negative x to the first, all that does is it flips this over the x-axis. So now your left end goes up and your right end goes down. If you look at a negative coefficient times x to an odd power greater than 1, the left end curves up and the right end curves down. It flips over the x-axis from the positive version. If you've got negative x to an even power, I bet you can guess both ends are going to curve in a downward fashion. Those are the end behaviors for polynomial functions, and they're determined by the leading term of your polynomial. So let's get some practice in here. So here we want to determine the leading term in the end behavior of the function shown on the screen, 3x squared minus 4x to the fifth plus 7x plus 3. We have to identify the leading term. The leading term is the term with the highest power. Okay? So in this case, the leading term is negative 4x to the fifth. So x to an odd power, remember, curves down on the left and up on the right, like x cubed. But if you multiply that by a negative, it simply flips over. So the left end curves up and the right end curves down. So that is our end behavior. As x goes to negative infinity, y goes to positive infinity. And on the right side, as x goes to positive infinity, y goes to negative infinity. If you graph this function, using some sort of software, you will see that the left end of the graph looks like this and the right end of the graph looks like this. And that's all we're focused on for now. We'll look at later how to figure out what happens in the middle. Let's try another example. So this one's a little bit different. This is a polynomial function, and the leading term is not obvious. The reason it's not obvious is because this is not simplified. It's factored, it's not simplified. We need to simplify to find the leading term. Okay? Now the good news is we don't actually have to multiply it all out. We're only interested in that leading term. So if we look at this, like we've got 2x times x minus 1 times x minus 1. We could multiply the x minus 1's together and then distribute the 2x and see what our leading term is, okay? But really all we're interested in is the leading term. So what we're going to do is I'm going to multiply the x minus 1's together, but I'm only going to keep track of the leading term of that. When I multiply those together, my first term, my highest degree term, is going to be x squared. And all of my other terms are going to have a lower degree. So I don't care what those are, so I'll just put something like plus dot dot dot. Insignificant terms as far as end behavior is concerned. And I'm going to carry down my 2x. Now I'm going to take my 2x times what's in the parentheses. In other words, I'm going to distribute it. So I get 2x cubed plus terms of lower degree. I don't care what they are because I'm just interested in the leading term, which is 2x to the third power, which is x to an odd power. So the left end grows in the negative direction, the right end grows in the positive direction, and I don't flip it over because my coefficient is not negative. So this is my end behavior for this polynomial function. Okay, another one that we have to simplify because this is all multiplied together. We have to multiply it together and find our leading term to get our end behavior. So using what we learned last time, I'm going to go ahead and multiply these first two together, negative x to the fourth. I'm going to distribute to give me a leading term there of negative 2x to the fifth. And I could multiply it by the negative 3, but that's going to be a lower power, so I don't care. I'm just going to say plus dot dot dot. I'm not interested in what that is. And then I'm going to look at this last part, x plus 5 to the 13th power. What that means is x plus 5 13 times multiplied together. You could look at that. You're going to have 13 of those. When you multiply all of those together, the leading term of all of those is going to be the x times the x times the x times the x times the x 13 times. So the leading term of that is going to be x to the 13th power. So what we end up with is negative 2x to the fifth power plus some smaller terms times x to the 13th power plus some smaller terms. Okay? Thank goodness we don't have to multiply out all those x plus 5s. So now all we have to do is multiply what's in blue by what's in red. And so I'll multiply those together. And that's going to give me negative 2x to the 18th power. That's x to an even power, which x to an even power goes up on both ends. But it's multiplied by a negative coefficient, so we're going to flip it over, and both ends are going to curve in a downward direction. As x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y also goes to negative infinity. And that's how you find the end behavior of a polynomial function.